Now it is time to talk about DES, Data Encryption Standard. Data Encryption Standard was designed by IBM in the late 1970s. It was based on an earlier design by Feistel. And so it was an answer to a call by NIST, but at that time the name of the NIST was somewhat different. So IBM responded to this call, which was to choose a cipher for federal use. So IBM sent DES to NIST. And in 1976, NSA tweaked the algorithm by changing its S boxes, but also changing its key length, and it became a standard. The block size of DES is 64 bits, so 8 bytes. Key length is 56 bits. Actually, it is 64 bits, but the parity bits of the bytes are not used for encryption. So effectively, it is 56 bits. This is important because when IBM designed an earlier cipher called Lucifer, the key length was 128 bits. So for this, this was their choice. But NSA shortened the key size so that since they had the better supercomputers at that time, their aim was to perform brute force attacks to this short key length, and I will show you how you can apply brute force attacks to short keys in a second. And the number of rounds were 16. So this was a Feistel type block cipher. Currently, it is known as data encryption algorithm, as shortened as DEA, because when we use keeping the word standard here, people still think that it is a standard and keep using it. So even today, a lot of people are using this, but actually they shouldn't. Anybody can break this if they have enough CPU or GPU power, and I will show you some numbers in a minute. So this is no longer standard and it shouldn't be used. But even in the big corporations or big web pages, when you ask for encryption, they give an example by talking about this. So you should be careful that not using this. Triple DES is a standard still, so this is why we are talking about this. But we are talking about this because it trained a generation of cryptographers. Crypto community learned a lot from the analysis of this. So it is always good to know how it is designed and what is the properties. But again, using it 3 times gives us triple DES, which is still a standard by NIST and ISO, which I will again talk in a minute. So DES became useless after 1990s since its short key was susceptible to brute force attacks. Let's talk about NSA involvement. In 1976, NSA tweaked IBM's initial design by changing DES S boxes, but didn't explain to IBM why they made such a change. IBM people analyzed this tweak and they discovered an attack that breaks the initial design, and they called it a T attack. They shared this discovery with NSA, and NSA asked them not to share this knowledge with public, for they had known this attack type for some time and were using it to listen to other countries. Biham and Shamir rediscovered this technique and called it differential cryptanalysis in 1990s. And this was the first public announcement of this technique because Japanese claimed that they even knew this technique during Second World War. But since secret agencies kept this knowledge to themselves, Biham and Shamir was made the first public announcement of this technique. So differential cryptanalysis is known by Biham and Shamir. And after the discovery of differential cryptanalysis, many different variants were introduced during all these years. Main idea in differential cryptanalysis is to find a weakness so that a small change in the input provides an anticipated change in the output with high probability. So let's look at the picture of this. As you can see, this is a Feistel cipher. We have left and right part. We have an initial permutation, but this has no cryptographic purpose. It is just to read the data in a good way for the hardware, DES chip in hardware. So for software, this has no importance. We have the round as follows. The right part is first. It is, since the block size is 64 bits, left and right parts are 32 bits. This 32 bits expanded to 48 bits. by expansion function. Then this 48 bits XORed with the 48-bit round key. Then we apply S boxes, the 48 bits, but the output is 32 bits. Finally, we apply a permutation to these 32 bits. So S boxes provide confusion, this permutation provides diffusion, and we XOR it with the left part. So this is a single round. We swap the left and right part and repeat this process 16 times. Key schedule is really simple. First, you eliminate the parity bits of the bytes in the 64-bit key, so you end up with 56-bit key, and you again divide it into left and right part, and you rotate it to left 1 bit or sometimes 2 bits, depending on which round you are working on. Then you have a second permutation. This permutation just changes the places of the bits, so it's a very simple permutation, and you obtain the round key here as K1, K2, and so on. So it is a very simple design, but now let's focus on this part, the round function part. So the picture is as follows. The right part, 32 bits, are expanded to 48 bits by actually duplicating 16 of the bits here. So you get a 48-bit here, XOR it with your round key. Then you perform 8 S boxes. These S boxes are all different. They take input as 6 bits, but provide 4-bit output. This way, your 48-bit input becomes 32-bit output after the SBox operation. So SBox is just a table lookup operation. We have the possible inputs and possible outputs. So inputs are 6 bits, so you have 2 to the 6 different possible inputs. And which input goes to which output is described by the definition of these SBoxes. So this, since you are substituting bits by bits, actually here you are providing the confusion. So this is our confusion layer in the cipher. Then the places of these bits are changed according to P permutation, and this is where we get the diffusion. So it is a simple design, but since we are working on bits, on software, it is a little bit hard to implement, especially if you haven't implemented a cryptographic algorithm before. Most probably you will implement it wrong in your first trial. So for this reason, we have test vectors in cryptography to check if we are implementing it correctly. So here's an example for this. If you are in the hexadecimal notation, if this is your plain text, 64 bits, and this is your secret key, then the round keys, 48-bit round keys will be here. From this key, this will be your round key. So if you don't obtain these results, this means that you implemented the key schedule in a wrong way. Then these are the output of your round function, 64 bits outputs, and at the end you get the ciphertext here. So again, if your implementation doesn't match with these ones, this means that you implemented in a wrong way. So most of the time we try to provide these test vectors when we design an algorithm so that people can be sure that their implementation works correctly. Let's look at security of this. In 1992, Biham and Shamir provided the first theoretical attack, differential cryptanalysis, on this, which requires less time than exhaustive search. Since the secret key is 56-bit, the exhaustive search requires 2 to the 56 encryptions, but their attack was faster. However, the attack required for you to capture a lot of plain text, which you choose actually. In this case, you needed to capture 2 to the 47 chosen plain text, which is unrealistic. This means that you are listening to the communication, you are capturing 2 to the 47 ciphertext, but you also know which plain text blocks they correspond to, and also these are not random plain text, but it is chosen due to a criteria you impose. As you can see, this is resistant to differential cryptanalysis, and Biham and Shamir was surprised about this. This is because these S boxes were changed by NSA, because IBM's initial design had worse S boxes, and the differential cryptanalysis could break it. This is why NSA tweaked these S boxes so that it became a better block cipher, so that people knowing this technique couldn't break it. But again, NSA made a good choice, but shortening the key make the algorithm weak. So in 1994, Matsui provided the first experimental cryptanalysis of DES by introducing linear cryptanalysis. Also in 1997, there was a project called DESSHAL. Around 78 PCs connected by the internet tried to perform a brute force attack, and they deciphered they captured the DES key for the first time in public. And there was also a machine specifically built for DES key breaking. So it's called DES Cracker. This was a machine containing around 2,000 custom chips, and this could break a DES key in 56 hours. So in 1999, DES is only allowed in legacy systems, and people were encouraged to transition, move on to triple DES. And in 2002, Advanced Encryption Standard became effective. So people should be stopped using DES at 2002, but it is almost 20 years later now, and people are still using DES. So this is why it is important to give this message to everybody. You cannot use DES, sorry. So let's talk about DES variants and triple DES. DES was deployed in many applications, and it wasn't easy to change it with another cipher. In order to overcome the exhaustive search for 56-bit key DES, multiple DES encryption with different keys are suggested, but the expected security level is not possible in practice. For example, double encryption with 2 different DES keys does not provide you 112-bit security. Instead, it provides you 57-bit security, which is not that good. Currently, the most used DES variant, which is also standardized by NIST and ISO, is the triple DES algorithm. In the triple DES, the idea is as follows. You choose 3 different DES keys. So you first use DES in the encryption mode. You encrypt your plaintext with your first key, but the result is no longer your ciphertext. You again feed it to DES, but this time you perform the encryption operation, but not with K1, but another key, K2. And finally, you perform the third encryption with the secret key, K3, and you obtain the ciphertext. This is why encryption, decryption, encryption representation here. So this way, actually, you are using 168-bit keys in total, 3 times 56. But in practice, triple DES actually provides 112-bit security. So let's talk a little bit about triple DES. It has backward compatibility because if you choose all the 3 keys equal to each other, then triple DES becomes identical to DES. Let's go back to previous picture and see why this is the case. Assume that key 1, key 2, and key 3 are all the same. When you perform triple DES encryption like here, first you encrypt plain text here on a plain ciphertext, but then you decrypt with the same key. So you return back the plain text and then perform the third encryption, but this time it is like a single DES encryption. So you end up with this triple DES turns into a single DES. So this is why, in order to have backward compatibility, we use encryption, decryption, encryption. You may choose encryption, encryption, encryption. This has the same security, but does not have backward compatibility. So a strange thing happened that, and NIST actually said that using algorithms with 112-bit security is secure until 2030. But recently they made an announcement that triple DES will no longer be NIST standard after 2024. So we can see that NIST is trying to keep a distance, their distance with DES and triple DES. So we will see how this choice will affect them in the future, because in Turkey, many credit cards uses triple DES for contactless payments. So if you have a credit card that you can pay in a contactless way, either there's AES in it or triple DES. We tried to check every credit card in Turkey and observed that more than half of them actually using triple DES. So I'm wondering what happens after 2024. For instance, if you go to United States and use a Turkish credit card with triple DES encryption algorithm there, I wonder what would happen if you try to pay it as a contactless payment. I wonder if the device would accept your payment or not. So we will see what happens 3 years later. Okay, but in order to check which algorithm your any smart card or your credit card uses, actually you need a device called, most probably, I mean, there are other devices, but Proxmark is the most famous one. You can use that kind of devices to interact with your NFC devices. You can also use your mobile phones that have NFC capability. If it is an Android mobile phone, then you can use that NFC. If it is iPhone, you're not allowed to use it. But if it is an Android phone, you can install some app and check what kind of smart card your credit card or any other smart card you're using has inside it, the chip model and so on. But I should warn you that those programs are sometimes give wrong results. For instance, they say that this smart card is MyFair Classic 1K, but in practice it is not. So it turned out to be it uses triple this instead. So just I'm trying to warn you that don't trust all of the NFC applications that are available for Android. Okay, you using a Proxmark would give you correct results. So we talk a lot about saying that the key size was short. So a natural question arises, what should be the key size? An attacker that captures a single ciphertext can try to decrypt it with every possible key to check if it provides a meaningful plaintext, right? So just listening to the communication and capturing a single ciphertext block, you have the ability to perform an exhaustive search attack. Such an attack is called an exhaustive search or brute force attack. This is a generic attack. In other words, it is valid for every cipher. It doesn't matter if you're using DES or AES or any other block cipher, you can always try every possible key. This is a brute force attack. For a key-bit keyed cipher, the attacker is required to perform at most 2 to the k encryptions and decryptions. So this is your time complexity. Thus, security of a block cipher is upper bounded by exhaustive search. In other words, 2 to the k encryptions is your upper bound. You cannot have better security than k-bit security. So when I say 100-bit security, this means that we can break it by performing 2 to the 100 encryptions and so on. So this quantity is referred to as time complexity. So let me show you how hard it is to perform the exhaustive search. So this has 56-bit key. This means that if we have 2 to the 56 different keys, so these are the total number of keys that you can have. But if you move to 80-bit security, the number of possible keys becomes now this. So it increases exponentially. For current standards like AES, the smallest key size you can have 128 bits. So this number is this. For 192, this. And for 256, this is the number of possible keys. So a natural question to ask is, so how long does it take for me to perform this many encryptions, right? So you can use your CPUs to perform exhaustive search. Today we have very fast CPUs, but they are not fast enough to perform 2 to the 56 operations in a reasonable time. So instead you can use GPUs, and because GPUs may perform from 10 to 100 times faster than CPUs, because GPUs have a lot of cores, and you can perform parallel operations on the GPUs in a more efficient way. FPGAs are somewhat similar, but these are hardware, and not everybody has knowledge about them, so you cannot just buy them and use them. You need some knowledge. But CPUs and GPUs are not the same, because you already have them with your computer, with your laptop. So just by writing some code or just downloading an executable, you can perform an exhaustive search attack on these devices. But once you have a very good hardware implementation, if you burn it to the silicon and make a dedicated device just to perform this attack, this means that you will actually building an ASIC, and these are more cost-effective compared to GPUs or CPUs, and this is what actually Bitcoin miners are using. So by using ASICs, 2 to the 56 should be really easy. For instance, for GPUs, we can perform 2 to the 32 encryptions or search this many keys in a second for many block ciphers. And a year has like 2 to the 24 seconds. So if you multiply it with this one, this means that with a single GPU, it will take a few months for you to break this. So if you have hundreds of GPUs, you can capture the desk key in a few hours. If you have more or people on the internet connect to each other and try to break a desk key, you can even perform it in a few seconds. So this is why you should avoid short keys. And 2 to the 8 is not that reachable, but still it is a practical attack might be performed by a lot of GPUs or with ASICs. So this is why I recommend always using at least 128-bit key for symmetric key encryption algorithms. Otherwise, you wouldn't have much security at all. So if the computers gets if the technology gets really good, and assume that by using every device in the world, we can perform 2 to the 128 encryptions in a second. So assume that we can capture a 128-bit key in a second. But then this key length would still be secure, because even if you have that much power, performing an exhaustive search attack to this many keys would take millions or billions of years. So before you can finish performing an attack on 2 to the 256, so trying to capture 256-bit key, before you capture the key, most probably the end of the universe would come. So, and of course, we are assuming that you can pay the electricity bill. Okay, so this is why these key lengths are secure. If not any huge technological advancements occurs, these key lengths would give you a long time security, and you shouldn't need to worry about the key length if your algorithm you are using is secure.